we need to describe the concept of the light clock. What we have is a clock which is made by the journey of light. A piece of light, a photon of light, starts from the top, goes down and goes up again. And that corresponds to one tick. So it basically reflects between these two mirrors. Goes to this point, goes down and goes up again. This is one tick of the clock. We know the speed that it travels is going to be the distance divided by the time. Or in other words, the time is equal to the distance divided by the speed. So the time is the time taken for one tick from there to there. That is the distance here, and the speed is obviously going to be the speed of light. Now we need to define the proper time interval. Proper time. Proper time is the time measured by an observer in a frame of reference where the events take place at the same point in space relative to the observer. We have, this is our clock here, and our clock is not moving. This is in a frame of reference which is moving relative to ours. So as far as we're concerned, this is measuring proper time. This is the journey that I take to get from home to Copenhagen. We have two people that are measuring this time. There's Mrs. Dr. Brogfam with her stopwatch, and there's Mr. Bolton with his stopwatch. Who is measuring proper time? Well, as far as Dr. Brogfam is concerned, I start in Scheveningen, I go all the way down here, and then I end up in Copenhagen. These two events, my departure and my arrival, as far as she is concerned, happen in different places, so she does not measure proper time. For me, however, then on the platform in Scheveningen, the door of the train opens, I step on the train. 1 hour later, I'm in the same place, the same train, I step off, I step backwards again, and I end up in Österport. These two events have happened at the same place. They happen at the door of the train. So I measure for time. Now there is this super fast particle called a meson or pion, which travels across the lab at 95% of the speed of light. There it goes. The question is, we have to look at this. The length of the lab is roughly, let's say, 10 meters. Who is moving, the pion or the lab? Well, it's both. Both are moving depending on your point of view. As far as the pion is concerned, the lab is moving relative to it. As far as the lab is concerned, the pion is moving. How much time does it take? Here again, that depends on your point of reference. Depends who's timing it and in what frame of reference that clock is still. Now the time is the distance divided by speed. Now you're not going to agree on time. You will agree on speed, but you will not necessarily agree on distance. Now let's say the time taken for us, let's say we have a stop clock and we measure it. The time taken for the pion to get across is 3.5 times 10 to the minus 8 seconds. It travels this distance, which is 10 meters, in 0.95 times the speed of light. In other words, 0.95 times 3 times 10 to the 8 time. And we find out that the time is 3.5 times 10 to the negative 8 seconds. However, the pion is a not very stable particle, and there's no way that it's going to last that time. Yet, we know that we can detect it here, and we can detect it at the other side of the lab, when it shouldn't have lived for that long. Now, the only way that it could have lived for that long is that if its lifetime, if its clock were going slower than ours. So its moving clock must be going slower than ours. So its value for time is going to be less. It also means that this value for the distance is going to be less. It doesn't measure 10 meters as the length of the lab, it measures a shorter distance. Who measures proper time? Well, since where are the two events? Well, the two events are basically the beginning and end of the journey. So really, who measures proper time? It's the pion that's measuring proper time, because the start and the finish happen at the same place. As far as I'm concerned, the start and the finish are in different places. So the pi meson measures proper time. The absolute sandwich. How long does it take to make a sandwich? Let's say we have a relativistic sandwich bar. On this sandwich bar, in proper time, the clock, you start the clock, you start making the sandwich, it takes 3 minutes to make the sandwich. Fine. So this is your sandwich bar. 3 minutes later, you have the sandwich. Perfect. But what about a relativistic sandwich bar? Now we know that moving clocks go slow. So this is a sandwich being made in this sandwich bar, which is moving relative to us. So the relativistic sandwich bar, we know on the sandwich bar clock it takes 3 minutes. But we're not going to agree on time. But what's going to happen is that we're going to measure on our clock 5 minutes are going to go past. So on the clock, which is stationary relative to us, we measure 5 minutes. So we look at the clock on the sandwich bar. It appears to be running slow. We've measured 5 minutes, and this has only gone past 3 minutes. Who is measuring proper time? Well, where do the two events happen at the same place? When the proper time is measured by an observer in a frame of reference where the events take place at the same point in space relative to the observer. So the starting and the finishing of the creation of the sandwich happens at the same point relative to the person making the sandwich on the sandwich bar, and not relative to me, because they start and they finish at different places. There's this fun, there's an excellent video here showing
two spaceships are traveling together through the galaxy at close to the speed of light. Mounted on one ship is a laser that can fire pulses of light, and on the other, a mirror. The pilot of the first ship fires a pulse at the mirror and watches as it is reflected back. A clock on board measures how long the round trip takes. But now suppose that he does this as the ships are passing an observer on a nearby asteroid. According to relativity theory, this observer sees the pulse moving through space at exactly the same speed that the pilot does, namely the speed of light. But he also sees the pulse traveling a longer distance, because from his perspective he must add the forward motion of the ships to the motion of the pulse between them. So he measures a longer time interval for this round trip than the pilot does, because he's watching the pulse go farther without going any faster. This effect is called time dilation. If two observers are moving with respect to one another, each perceives that the other's time is flowing more slowly.
An illustration of this point. Now, the time dilation formula, you need to be able to derive this. We have our light clock. The pulse is going from the top to the bottom to the top again. So it's basically the same point in space. What if this light clock is moving in another frame of reference? So this is basically what we're going to see. We actually see that in this same period of time it actually travels a further distance. The only way it could travel a further distance is if it takes more time, because everybody must agree on the same speed of light. So this is a greater distance, so it's going to take a greater time. So since the light has further to go, it's going to be a longer time between talks. So in other means, the clock measured in the other frame of reference is going to be, the moving clock is going to be going slower than mine. And what is the relationship between this, and this height here, this length here? Well, it's basically Pythagoras. So basically by using Pythagoras we can derive the time dilation formula. This is the length, this is Vt, L. The point of this is that we know that this squared plus this squared will be equal to L prime squared.